everyone, this is the video for class 26 of PH 125, and today we're going to be continuing to talk about simple harmonic motion. We're going to do a quick review of a mass on a spring, and then we're going to move on to talking about the oscillations of a pendulum, and then we're going to wrap up today by doing an introduction to waves. Okay, so just a quick reminder about simple harmonic motion of a mass on a spring. Here I have different snapshots of the mass on a spring oscillating as a function of time. And remember that the oscillations of a mass on a spring are due to the restoring force, which is the force of the spring acting on the mass. And we know that the force of the spring acting on the mass is equal to minus kx, where x is the displacement from equilibrium. And so x is set to be equal to 0 at that equilibrium position. Okay, and then we learned last time that the period of oscillation is 2 pi square root of m divided by k. We also learned that the frequency of oscillation is just the inverse of that period, so that would be 1 over 2 pi square root of k divided by m. And the angular frequency is the frequency multiplied by 2 pi, and so we just end up with the square root of k divided by m. Okay, so now let's take a closer look at these snapshots of the oscillating mass on a spring as a function of time. So this top snapshot here, the spring is stretched so that the mass is at position plus a, where a then becomes the amplitude of the oscillation. At that moment in time, we know the velocity is equal to 0 and the acceleration is in the same direction as the force, which is pulling back towards that equilibrium position. And now thinking about energy, because our potential energy due to a spring is 1/2 kx squared, we know that whenever x is at its maximum magnitude, so that would mean whenever the magnitude of x is equal to a, we get maximum potential energy, right? Because 1/2 kx squared. Okay, and so then what that means is we also have kinetic energy equal to 0. So there's a few ways of thinking about it. First way to think about it is that we know the velocity is equal to 0 right at that moment in time. And so that already just tells us right there that the kinetic energy has to be 0, since kinetic energy is 1/2 mv squared. All right, the other way to think about it is thinking about conservation of energy. So the total energy of the system is always constant. So we know then that if at some point where we have our maximum potential energy, that has to be where the kinetic energy is equal to 0, since the total energy is U plus K. Okay, and so then the next snapshot in time, our mass has moved to the equilibrium position. Right at this moment in time, the acceleration has to be 0 since the restoring force is 0. And at this point, we also have V, which is going to be negative. So the block is moving to the left. All right. We can now think about the energy at this moment in time. So because the spring, the mass is at that equilibrium position, we know U is equal to 1/2 k times 0 squared. And so then the potential energy due to the spring right at that moment in time is going to be equal to 0. Since the potential energy is equal to 0, that means that the kinetic energy is going to be at a maximum. And so then that means that the velocity will also be at a maximum right as that spring goes through its equilibrium position. Now, as the spring continues to oscillate, we end up with some position, x equals minus a, so this is going to be the maximum compression of the spring. Again, the potential energy is going to be maximized because it's 1/2 kx squared. So here we have the maximum value, the maximum magnitude of x. Since x gets squared, the fact that it's negative doesn't come into play in terms of the potential energy, right? It's always just going to be a positive value, 1/2 k a squared in this case. All right, and we know then that V is equal to 0, so K must also be equal to 0. At that moment in time, the spring turns around, and so it will start pushing back towards the equilibrium position. And that tells us then that the acceleration right at that third time point must be pulling back towards the equilibrium position, so it must be in the positive direction. Okay, so then our next moment in time, we end up with the block passing back through equilibrium, but now it's traveling in the opposite direction. Once again, potential energy is 0 since x equals 0, and that tells us that the kinetic energy and the velocity are maximized. So this would be the magnitude of the velocity. Okay, and then finally we return to our starting point, so that's that maximum stretch to x equals a. And once again, you have maximum potential energy, minimum kinetic energy. Okay, and so then by conservation of energy, we can automatically calculate the total energy of the system if we know that maximum amplitude of oscillation, because then we know U max, right? It's going to be 1/2 Ka squared. And that's useful to us because then at any given time, we know that the total energy is always equal to 1/2 Ka squared. And so you can think about the potential energy if you know the position of the spring, or you could think about the kinetic energy if you know the velocity of the mass on a spring at any given time, and then you would be able to calculate either the potential or kinetic energy, use the total energy to find the other. Okay, all right. So that pretty much wraps it up for a mass on a spring. Now let's talk a little bit about a pendulum. We introduced this last time, and we determined since the system is disturbed from equilibrium by some amount x, we said that the net force acting in the x direction is what acts as the restoring force in this case. So it turns out that that's going to be the x component of the tension in the string. So that's the force that's pulling the mass back towards its equilibrium position at x equals 0 here. Okay, we used this small angle approximation, which is up in this black box, that sine of theta is approximately theta in radians for small angles, and cosine of theta is approximately 1 for small angles. And what we found is that then the restoring force can be approximated by the weight of the bob, so that's mg, multiplied by theta, that angular displacement of the bob. Okay, and so now we're ready to talk about the period of oscillation of a pendulum. So to get there, we want to think about that restoring force. Remember, we just said that it's approximately equal to the weight of the bob times the angular displacement. Looking at our graph, if we want to think about this restoring force in terms of x, so that's that linear displacement from equilibrium, rather than thinking about it in terms of theta, which is that angular displacement from equilibrium, what we can do is use the arc length formula. So here we know that arc length S is equal to R times theta. In our case, looking at the diagram I have on the left-hand side, that means that X, which would be kind of like our arc length, is going to be equal to the radius, which is L for us, times theta here. Another way to think about it is by looking at our angle. X is going to be the opposite to that angle, right? And so then we would have sine of theta is equal to x divided by L. And once again, we can use that small angle approximation, that sine of theta is approximately theta. And so we would get theta is equal to x divided by L, and that gives us the same relationship that x is equal to L times theta. So either way that you want to think about it will work here. And so then what we can do is we just plug in that relationship for theta. Theta is equal to x over L. We just plug that into our restoring force that we already derived, and we get F is approximately equal to mg x divided by L. Now I'm just going to reorganize it, and I'm going to put all of the constants that get multiplied by x. I'm just going to group those all together. And then we get something that looks like F is proportional to x. So F is equal to some constant times x. And that reminds me a lot of our restoring force for a spring, right? So the magnitude of that force was equal to K times x, where K was some constant. And so what that means is that for a pendulum, we can think about that constant out in front of the x as mg divided by L. Okay. So then with that in mind, it's pretty straightforward to derive the period of oscillation of the pendulum, because we can look back at the period of oscillation for a mass on a spring. It was 2 pi the square root of m divided by k, and that was for a restoring force F equals k times x. And so now what we're going to do is just go ahead and replace k, the constant that gets multiplied by x. We're just going to replace it with our constant for a pendulum, which is mg divided by L. So we can plug that in, get some cancellation. The m's should cancel here, and I can take the L, which is in the denominator of the denominator, and move it up into the numerator. And we just get that the period is equal to 2 pi the square root of L, so that's the length of the pendulum, divided by g. Okay, and so quick tiny story here. This was first derived by Galileo, this relationship, and he actually thought about it when he was sitting in church. He was staring up at the chandeliers, and he noticed that the chandeliers with equal lengths oscillated at the same rate. And so this didn't depend on the mass of the chandelier, it only depended on the length. And so this is how he came up with this idea that the period of oscillation of a pendulum should only depend on the length of the pendulum. And apparently he timed the period of oscillation by counting his pulse. So just a little kind of, historical detail there. All right. So with that in mind, let's go ahead and think about the angular frequency of a simple pendulum. What would the angular frequency be? Okay, so the key here is we already know that t is equal to 2 pi square root of L divided by g, and we just need to remember that the angular frequency is equal to 2 pi divided by the period t. Or in other words, I always actually think about it as 2 pi f, where f is the frequency and then the frequency is 1 over t. They're equivalent, but I always memorize 2 pi f for some reason. So anyway, what that means, we get cancellation of the 2 pi's. We end up with 1 divided by the square root of L divided by g. G is in the denominator of the denominator, and so it can come up into the numerator, and we end up with omega equal to the square root of g divided by L. So I would go ahead and pick answer D here. One more. So suppose you have a grandfather clock and it's running too slow. We want to know, how would you make it run on time? What do you need to do to the pendulum? So we want to think about, what do we need to do to make it keep accurate time instead of keeping time too slow? All right, so once again, the key here is just going to be remembering the period of oscillation of the pendulum is equal to 2 pi square root of L divided by g. And if the clock is running too slow, what that means is that the period of oscillation, the period of the clock, is actually too long, right? So like 1 second is lasting too long. It's lasting longer than 1 actual second. And so what we need to do is we need to change the period of oscillation so that it's shorter. And that will help us to get the clock to run on time. And so how do we make the period of oscillation shorter? Well, we just need to shorten the length of the pendulum. And so I would pick answer B here. We need to make the pendulum shorter. Okay, so then just to summarize what we've learned so far, remember the restoring force for a pendulum is equal to mg theta, where theta is the angular displacement, and it can also be rewritten as mg divided by L times x. Then we know the period of oscillation was 2 pi times the square root of L divided by g, so it's independent of the mass of the pendulum. And with that information, we can calculate the frequency because frequency is 1 over period. And we can also calculate the angular frequency because omega is just 2 pi divided by the period. Okay, so now let's think about energy considerations by analyzing the motion of the pendulum as it oscillates back and forth. So, first of all, at either of the 2 highest peaks of our pendulum, so either as it swings left or as it swings right and it reaches its maximum height, what happens here? So in either of those 2 cases, we can think about the amplitude in the y direction. So the maximum displacement from the height when the pendulum is in equilibrium. So that would be reached right at those end points, right? So it's the highest height corresponds to the maximum displacement in the x direction from equilibrium as well. So in other words, the x displacement of the pendulum is either going to be minus ax or plus ax, so plus or minus the maximum amplitude from equilibrium. Those x amplitudes are what you would use if you were thinking about the position, x position as a function of time, thinking back to those simple harmonic motion equations that we derived at the very beginning of this chapter. Okay, so we're at this maximum height when we're at those 2 endpoints, and so that tells us that we must have maximum gravitational potential energy, because gravitational potential energy is equal to mgy, and so if we let y equal 0 at the bottom of the swing, so right at that equilibrium position, then we know that we're at a maximum height, and so we must have maximum potential energy right at the 2 endpoints of the oscillation. Okay, and so since the potential energy is maximum, that must correspond to the point in time when the total speed is 0 because the kinetic energy is also 0. So what that means is that the velocity in both the x and y directions will be 0 right at that time. So the pendulum is changing in direction both in terms of plus or minus y direction and also in terms of plus or minus x. So it's turning around both in terms of x and y directions. And so both the velocity in the x and y direction will be 0 right at that time point. Okay, and then what about when the bob goes back through equilibrium? So that's when we set y equals 0 to be right at that equilibrium position, so y will be equal to 0. x is also equal to 0 at that point. And so then, since y is equal to 0, we know the potential energy due to gravity will also be 0 there. And so that means we must have maximum kinetic energy. Since kinetic energy is 1/2 mv squared, that means we must also have maximum speed right at that point. So the speed, which is the magnitude of the velocity, remember that's going to be like the square root of vx squared plus vy squared. This is the overall speed. It must be a maximum here. Okay, so putting this all together and thinking about conservation of energy, if we know the amplitude of the oscillation in the y direction, so how high the pendulum swings above that equilibrium position, then we can calculate the maximum potential energy. It will just be mg times ay. And then we know that that must be equal to the total energy at any point in time. So that must also be equal then to the maximum kinetic energy at the point in time when the potential energy is equal to 0. So in other words, as the bob swings through that equilibrium position, we know the kinetic energy must be equal to that maximum value of potential energy, since that's equal to the total energy, right? So U is equal to 0, so K is equal to the total energy E. All right, and then of course we know that that's also equal to the potential energy at those turning points of the pendulum, so the points of maximum height in terms of the oscillation of the pendulum. Okay, so far we've really been talking about a simple pendulum. So remember, this is this idea that we have a concentrated mass at the end of a weightless string or rod. But we can also think about things oscillating like a pendulum that have mass distributed throughout the thing that's oscillating, right? So not just concentrated at a little bob at the bottom. And this is what we refer to as a physical pendulum. So there are a few examples of physical pendula over here on the right-hand side. Here we have a disc that can oscillate back and forth on some line that's sent through the center of the disc towards the top of the disc. We could also have a rod that oscillates back and forth, or we can also think about bones as oscillating physical pendula. Okay, and so then it turns out that the period of oscillation for a physical pendulum, it's similar to the period of oscillation for a simple pendulum. Remember, that was 2 pi square root of L divided by G. Here it's a little bit more complicated. So it's 2 pi times the square root of little l divided by G, where little l is the distance from the axis of rotation of the pendulum to the center of mass of the thing that's oscillating, right? So the center of mass of that physical pendulum. So we still have that factor, but then we also multiply by this additional factor that I have in parentheses. So it's the square root of I, the moment of inertia of the pendulum, divided by m little l squared. So again, L is that distance from the pivot point to the center of mass. Okay, so since we have 2 square roots multiplied together, we could actually just put it all under 1 square root. One factor of L would cancel, and we would just be left with I divided by GML. The reason why it's separated out here is so that it looks similar to our simple pendulum multiplied by some little factor here. Okay, and we'll do an example with that in class. We won't be dealing too much with simple pendula though. All right, so the next topic, and really the second to last topic for oscillations, so for chapter 13, simple harmonic motion, is damped oscillation. So far we've really been considering oscillations where we have no friction. So there's no friction in our spring, we have no air resistance for our pendulum, but normally we will have some friction. So it's pretty much unavoidable. In general, there will be some friction present. And so when we don't have friction, we refer to this simple harmonic motion as undamped, or we say that there's no damping. But when we do have friction, then we refer to it as damped oscillation. So there are a few different examples of damped oscillation. The first one is just where we have the amplitude of oscillation decreasing with time, but we continue to have oscillations. And this is referred to as underdamped oscillation. So that would be this example in the middle here. So you can see that the position as a function of time, it continues to oscillate, but the amplitude is decreased as a function of time. So that amplitude of oscillation. Don't worry too much about this equation. You will not be asked to use it. This is just an example. We will have friction in any lab setting. So in any sort of lab experiment, you would see probably underdamped or overdamped oscillations. critically damped or overdamped oscillations, that means that actually the amplitude decreases as a function of time, but you no longer have any oscillations. So you can see here that the amplitude, the x position as a function of time, it's just like a smooth curve. We don't have any oscillations there. All right, now we're finally on the last topic for chapter 13, which is driven oscillations and resonance. So it turns out that if you have an object like a mass on a spring, that period of oscillation that we calculate, that's like the preferred period of oscillation for the mass on a spring. So we refer to it as the natural period, or if we're talking about the frequency, which is 1 over the period, we would refer to it as the natural frequency, which we usually call F naught. Okay, you might also hear it called the resonance frequency. So what happens is, like, if you think about a mass on a spring, you could push on a mass on a spring and cause it to oscillate at a different frequency. So if you're literally holding the mass and oscillating it, you could make it oscillate at a different frequency. But you're going to get the biggest response, so that means the biggest amplitude of oscillation, if you try to make it oscillate at its desired frequency, so at its natural frequency. Okay, and so this is a property referred to as resonance. This is how your radio works. So radio waves have a frequency, and electronics in your radio has a preferred frequency as well. And so all of the radio waves are in the air all the time, but you only pick up the radio waves that have the frequency that is the same as the frequency that your radio is tuned to be its natural frequency or its resonant frequency. That means you get the biggest amplitude response at that frequency, and that's why you pick up the radio station that you're looking for. All right, I will also mention that this plays a huge role in MRI, which is my field of research, so I had to throw it in there. It turns out we drive the oscillations of the protons in the body so that they oscillate at their resonant frequency, and that gives a big amplitude response that we can actually pick up and measure. Okay, and then one last kind of scary example here. This would be an example of a pendulum being driven at its resonant frequency. So the Tacoma Narrows Bridge, also called Galloping Gertie, it got driven by wind at exactly its resonant frequency. And so there was this huge collapse because we got this huge amplitude of oscillation, the bridge swinging back and forth, because the wind drove it at exactly its resonant frequency, and it broke. It was very scary. This happened a long time ago. But anyway, so these are examples of resonance. All right, so that's the end of chapter 13. It's all about simple harmonic motion. Next, we're kind of just going to expand on this idea, and we're going to be talking about waves and sound. Okay, so as I mentioned, we're moving on to chapter 14 now, which is all about waves and sound. And we're just going to get started by thinking about waves. So what is a wave? It's something that we all experience, but it's a little bit hard to talk about, actually. But one way to think about a wave is just a disturbance that propagates, or in other words, it travels from one location to another. Okay, so what are some other properties of waves that will help us kind of understand this definition a little bit better? First of all, the speed of a wave depends on the medium that it's traveling through. So a wave traveling through a solid will be have a different speed than a wave traveling through a liquid or a gas. Okay. Waves also carry energy and momentum. So this is another characteristic property of waves. And so then the thing that's really propagating from one place to another, I tend to think about it as energy. So energy is the thing that's getting transferred or traveling from one location to another when we think about a wave that's propagating. And that goes hand in hand with the fact that when you think about a wave, it's not actually the particles in the medium that are getting transferred from place to place. It's the energy that gets transferred from place to place. So the particles that in the matter that the wave is propagating through, they will oscillate around a little bit, they'll move a little bit, but they won't actually travel like the wave does. So if you think about a wave, a physical wave of people, in a stadium, something like that, you're moving up and down, but you're not like running around the stadium with the wave, right? So that's an example of thinking about the fact that the thing that's propagating the wave, the medium, the matter usually is what we're thinking about, but here we're thinking about people. That matter doesn't actually travel with the wave. It just oscillates back and forth a little bit. Okay, and so ways that we can characterize waves, we usually think about two different types of waves, so transverse waves and longitudinal waves. We'll start with transverse waves here. And so in a transverse wave, the displacement of the particles that propagate the wave is perpendicular to the direction of propagation of the wave. So here, if we think about this string, the string itself oscillates up and down as the wave travels along the string, but the wave travels left to right. So that would be a perpendicular oscillation of the string relative to the direction of the wave. So this would be a transverse wave. So examples, waves on a string, also light and radio waves. These are both forms of electromagnetic radiation. That's a topic for next semester. You can look forward to that. But these are both transverse waves. And ocean waves, kind of. Okay, so kind of. They go up and down, but it turns out they also are longitudinal waves. They also oscillate in the same direction as the propagation direction of the wave. So a simpler way to think about a longitudinal wave is to think about a wave transmitted along a slinky. So if you've ever played with a slinky and you like kind of just push it in a little bit, you get these propagation of these little compressions of the slinky and stretches of the slinky along the wave. So we call those compressions and rarefactions. Don't worry, we'll do a little bit more on that later. But the basic idea is that the actual individual coils in the slinky, that's what we can think about as propagating the wave. They oscillate back and forth in like the left to right direction, which is the same direction as the propagation direction of the wave. And so this is why we would refer to that type of wave as a longitudinal wave. Other examples of longitudinal waves, the classic is sound, which we will be talking about later on in this chapter. Also the slinky, and if you think about it, in the ocean you bob up and down, but you also kind of move left to right. And so it's a combination of both a transverse wave and a longitudinal wave. Okay, so to wrap up for today, when people do the wave in like a stadium at a sporting event, what type of wave is it? Okay, so when you do the wave, you bob up and down, but the wave travels side to side, right? So I would say that this is going to be a transverse wave B here. All right, that wraps it up for today, and I will see you guys in class.